Welcome to another lesson. Today we're going to be covering different types of graphical representations that we can use to summarize data. We're going to be going over line graphs, bar charts, dot plots, pie charts, and lastly the stem and leaf plot. A line graph is typically used to present some characteristic that you're recording over time, and the key phrase is recorded over time. So for example, if you look at the graph on your screen, what we're doing is we're recording John's weight over 5 years, where John's weight is in kilograms. Now, the first thing that's going to pop out to you when you look at this graph is that John's weight is in fact increasing across the 5 years. And that's the real beauty of taking data and putting it into a graphical representation. Your brain actually interprets pictures a lot more easy and a lot faster than it would if you had to look at a table. Graphical representation also makes it a lot easier for you to pick up on trends or patterns in the data. Looking at this example, we can clearly see that John maintained the same weight in 1993 and 1994. We can see that his lowest weight was recorded in 1991 and his highest weight was recorded in 1995. Looking at an example where we are looking at ice cream sales recorded across a week, we have the days of the week and we have the sales in the table that you can see on your screen. Now, if we wanted to take this data and transform it into a line graph, there are a few steps that we have to follow. Firstly, we need to identify the independent and dependent variable that we're working with. Now, these terms typically would have come up in one of your maths lessons, and the definitions are exactly the same as it was then. Your independent variable does not rely on any other variable, and your dependent variable relies or depends on other variables. So before you can actually identify which is your independent and your dependent variable, the question you need to ask yourself is, what are my variables? And in this example, your variables are the days of the week and sales. So we have two variables. To identify which is your independent and which is your dependent variable, you have to question, does the days of the week depend on sales? And what I'm asking is, does the day of the week change depending on the sale recorded for that day? And it's not as straightforward as it sounds, so think about what I've just asked. And the next question you need to ask is, does sales depend on the day of the week? So the question there is, depending on the day of the week that we're looking at, does the sales value change? And I want you to think about that, and we're going to answer that in a little bit. The next thing you want to do is you want to draw your axes, where y is your dependent variable and x is your independent variable. Finally, you want to plot your x and y coordinates and join it using a line. Okay, so to answer that question I just asked you, does the day of the week change depending on a sale value? Now, it's not as straightforward as it sounds. You have to think about this. If today is Monday going to suddenly change depending on whether I've made 200 or 500? And the answer is no. The day of the week isn't going to change. It's a constant. It's going to happen sequentially in the exact same order that it's always happened in. And here's a helpful hint. Whenever you're asking this question, if you have time is always going to be your independent variable. Okay, does sales depend on the day of the week? And it's quite easy to actually see this. I made 400 and it's a Monday. I made 800 and it's a Friday. I made 850 and it's a Saturday. So it seems as if the day of the week is influencing our sales value. So that suggests to us that sales is dependent on the day of the week. So we've just identified our independent and our dependent variable. Next, we want to draw our axes where sales is on our y-axis and the day of the week is on our x-axis. The next step is we want to plot our x and y coordinates. So this is exactly the way you did it in maths. We're going to plot Monday 400, right? That's your x and your y coordinate. And we're going to do this by drawing a vertical line going up from Monday and a horizontal line coming across from 400. And where those lines intersect is where we plot our point. And we're going to do this for the remaining days of the week. And finally, we're going to join this using a line. And we can clearly see that the most amount of sales is occurring at the end of the week, so during the weekend, and the least amount of ice cream sales are occurring at the beginning of the week. Moving on, a bar chart or a bar graph is a chart that consists of rectangular bars, where these rectangular bars' heights are proportional to the value that it's representing. Now, a bar chart is used for comparing two or more values, and it's generally taken over time or under different conditions. The first bar chart that we're going to consider is the simple bar chart. Now, a simple bar chart has figures that are used to make comparisons, and these bars are typically vertical or horizontal, and only the totals are represented. So on your screen, we have an example of a simple bar chart where we're looking at revenue across 5 years. And we can clearly see that each bar is representing a specific total or a specific revenue for that specific year. Looking at this chart, we can see that revenue seems to be fluctuating. However, the highest revenue is in fact in 1995, with the lowest recorded revenue in 1991. The next bar chart we're going to consider is the component bar chart. Now, a component bar chart essentially takes that bar chart that we previously looked at and it breaks down that bar into different segments or components. And this becomes very useful when we don't just want to know the totals, but we want to know what went into making up that total. So our previous example, we had revenue across 5 years, but what made up revenue? And that's what a compound bar chart is, where we can now see how each of these different streams contributed to total revenue. A compound bar chart, sometimes referred to as a multiple bar chart, because it allows you to compare figures and it allows you to trace trends. The easiest way to think of this is if you take a simple bar chart and you take a component bar chart and you combine them, you're going to get a compound bar chart. From our previous example, you can see that the first bar is our revenue. So we still have that bar there. However, we now have two different bars representing rent and advertising, which is representing the components that go into making up that total revenue. And this makes it really easy to compare the different values and to pick up on trends. So for example, if we just focus on rent, we can clearly see that there is a slight increasing trend occurring across the 5 years. And if we look at revenue, we can see that, again, there is fluctuation. However, there is an increase from 1991 to 1995. The final bar chart that we're going to look at is the Pareto chart. A Pareto chart is a combination of a bar graph and a line graph. So it's considered to be a special type of bar chart. Now, your plotted values or your bars must be arranged in descending order, and the line that's going to accompany your bars is going to show the cumulative totals of each category. Now, on your screen, we're going to look at an example where we're looking at types of defects for shirts, maybe. And we can see that we have 5 categories or 5 types of defects, and we've arranged this in descending order. So we have the highest amount of defects on our left and the lowest amount of defects on our right. And the line is representing the cumulative totals, where the final category, being half defects, must sum to 100%. Now we're going to look at an example. It's the exact same example that we looked at previously, but now we're looking at the actual data and we're going to speak about how we actually come up with this Pareto chart. We can see in this table, we have our frequencies for each defect. Now we can go ahead and we can plot a bar chart as we normally would, just ensuring that we order this in descending order. Okay, now how do we actually come up with the line? So this is where we have to do some calculations. And the first thing that we want to do, if it's not given to you, you want to go ahead and you want to calculate the total number of defects. So we're going to do this by summing 23, 16, 10, 7, and 3 to get a total of 59. And then we're going to go ahead and for each category or for each defect, we're going to calculate the percentage. For button defects, we're going to take 23 divided by 59, which is our total, multiplied by 100 to get a percentage of 38.98%. and that tells us that button defects contribute approximately 39% of total defects. Next, for the pocket defects, we're going to do the exact same thing. However, remember we are calculating a cumulative total, and so we're going to sum the previous percentage. We're going to do the same thing for the collar and the sleeve defect, and as well for the cuff defect, ensuring that when we do this for our final category, we sum to 100%. If you're not summing to 100%, this suggests that you've made a calculation error somewhere, and you've possibly maybe even rounded off incorrectly. So this suggests that you need to go back and check your calculation. Next, we're just simply going to plot an additional y-axis to record our percentages, and we're going to plot our coordinates using those green values, so 38% to 100%, and joining that with a line, we now have a completed Pareto chart. A dot plot is a number line that we draw according to scale depending on the data that we're working with. The symbol X is plotted at the corresponding positions on the number line, where the number of X's is proportional to the frequency of that specific number occurring in the dataset. So if we have a number occurring only once, then we will plot a single X. However, if the number occurs more than once, then multiple X's will be plotted one above each other at the same position on the number line. This is an example of a dot plot, and you can see it makes it very easy to visualize the dataset. We can clearly see that numbers 3 and 7 occur 3 times and number 9 only occurs once. A dot plot is extremely useful when working with small datasets. However, when you're working with a larger dataset, a box plot may be more suitable. The next graph that we're going to consider is a pie chart. Now, a pie chart is a circular diagram that is divided into slices and is most commonly compared to a pizza, where each slice has an area that is proportional to the total that it's representing. Keeping with the pizza theme, let us look at a pie chart that represents the ingredients of a pizza. Okay, so taking a second to look at the chart itself and what each color is representing, we can see that the crust makes up, it seems, 50% of the pizza, just judging based on the visual we're looking at, followed by cheese, tomato sauce, sausage, and mushroom. Now, how do we in fact calculate the area that each slice represents? So this can simply be done by following the following instructions. Step 1, we want to convert each value to a percentage. So just as we did for the Pareto chart, we're going to get our total, we're going to divide each segment frequency by the total, and multiply by 100 to get that percentage. Step 2, we're going to use those calculated percentages to calculate the degrees for each item, and we do this by taking the percentage multiplied by 360. And finally, we're going to use a protractor to draw the pie chart. So looking at the data for the previous example, we see that we have our percentages already calculated, and using those percentages, we can calculate the degrees, and finally, using those degrees and a protractor, we can quite easily construct this pie chart. The final graph that we're going to consider in this video is the stem and leaf plot. Now, the stem and leaf plot is used for summarizing quantitative data in table format to assist in visualizing the shape of the dataset. Now, if you don't know the difference between quantitative and qualitative data, you can go ahead and check out a previous video where I point out the differences. This is an example of a stem and leaf plot, where we have numbers separated by a vertical line. Now, the numbers on our left are referred to as our stems, and the numbers on our right are referred to as the leaves. The leaf is the last digit of the number, and the stem contains the remaining digits. So, for example, we have the number 44, so we have 4 on the left and 4 on the right. However, if we have the number 106, we have 10 on the left and 6 on the right. Now, it's important to note that when you construct a stem and leaf plot, you must sort your data in ascending order first. So let's consider the following example. Given the data on your screen, how would we come up with a stem and leaf plot? Step 1, we want to sort our data in ascending order. Step 2, we need to determine what the stems and what the leaves will represent. And this is important because once we come up with this choice, we have to go ahead and write that down so that anybody who's trying to interpret our stem and leaf plot understands what we've done. So we need to go ahead and specify a key. Step 3, We want to draw that vertical line to separate our two columns where we have our stems on the left and our leaves on the right. Now it's very important to note this. Each stem can only be listed once, and the stems have to be in numerical order, even if the corresponding leaves are blank. If you don't understand what this means, it'll become a lot more clear when we look at an example. Leaves must be listed in ascending order from left to right within each row. Okay, so let's go ahead and follow those steps. Now, step 1 is done for us. Our data is in ascending order. Step 2, we're going to represent our stems as the tens and our leaves as the units. Step 3, our vertical line. Okay, so now we're going to go ahead and list our stems. And remember, it must be in ascending order, but it must also be in numeric order. So we have to include those numbers in between, even though they don't have a corresponding leaf for each stem. And finally, we have our key, where our key helps us to interpret the stem and leaf plot. Okay, so 5 line 1 means 51, and this tells us that the leaf represents our units and the stem represents our 10. Now, interpreting the stem and leaf plots, we can clearly see that all of the numbers except 1 are less than or equal to the number 88. So in conclusion, 16 of the 17 values are less than or equal to 88, and only one value is greater than 88. In the next example, we're going to consider two data sets and we're going to compare them using a back-to-back stem and leaf plot. So let us suppose that the fat content in grams for English breakfast and cold meat sandwiches are to be compared, where the data is listed below. So step 1, we want this in ascending order. Step 2, we want to go ahead and decide on what our stems are going to represent and what our leaves are going to represent. Step 3, we're going to go ahead and draw our vertical lines. And this is where it gets a bit different. So a back-to-back stem and leaf plot is exactly what it sounds like. We're going to be plotting back-to-back, where we have English breakfasts on the left and sandwiches on the right. And down the middle, we're going to have our stems. Okay, so we're going to go ahead and list those stems in ascending numeric order down the middle. And we're going to go ahead and list the sandwich fat content leaves on the right. And the breakfast content on the left. Okay, so the key is very important, especially for a back-to-back stem and leaf plot, because the way in which we read the data matters. So for example, if we're looking at sandwiches, we read from left to right, where 1 line 3 means 13 grams. However, if we're reading the breakfast, we read from right to left, where 1 line 3 means 31 grams. And this makes sense because for the sandwiches, our stems are on the left, but for the breakfast, our stems are on the right. So we read 1 line 2 as 12, but 4 line 1 as 14, not 41. Okay, so interpreting the stem and leaf plot, we can see that there seems to be a cluster of leaves towards the upper stems for sandwiches and a cluster of leaves towards the lower stems for breakfast. So this suggests to us that there is a higher fat content in English breakfast as compared to cold meat sandwiches. This brings us to the end of the lesson. I hope this has benefited you in some way. Please remember to like this video, subscribe, and hit that notification bell below.